Hello friends, welcome to another lecture on advanced concrete structures. And in the previous lectures we have seen the design steps for biaxial loaded column, in which the columns are subjected to biaxial moments, and we have seen steps for both the cases, that is short column and for long column. So today we will see the actual numerical which is asked in the university examination. So today we will see numerical on design of biaxial loaded columns, where columns are subjected to biaxial moments, and today we will see the case of long columns. So before starting, I would like to introduce myself. I am Amey Khedikar, working in the Department of Civil Engineering at Tulsiramji Gaikwad-Patil College of Engineering and Technology, Nagpur.
Friends, we will have a numerical now. So I'll read out the numerical and we will sort it out and try to understand the given data, and whatever the values are available with us, I'll try to sort it out. So I'll read first. Design a biaxially loaded, eccentrically loaded, braced rectangular column deforming into a single curvature. This word is very important, single curvature, for the following data. Okay, so in that axial load is given 2000 kilonewton. Then factored moment acting parallel to long direction, it is given. In the larger end moment at top 220 kilonewton meter, smaller end moment at bottom 170 kilonewton meter. Then factored moment acting parallel to shorter direction, in which first one, longer end moment at top 120 kilonewton meter, smaller end moment at bottom 70 kilonewton meter. Then unsupported length is also given. Then the unsupported length is also given. Okay. Then effective length in x direction, that is 7.5 effective length, and in x direction 7.5, in y 6. Column section is given 400 by 600. Okay, and grade of steel is 415, and environment is moderate. So this is the given data we have, and now we will try to design. Okay, so I'll write it down here. So we have given a biaxially eccentrically loaded braced rectangular column having dimension 400 by 600 mm, deforming into a single curvature, so that we have to use the plus value. In further steps I'll explain you. And factored load. Okay, so it is also factored, it is also factored, and it is also factored. So all the loads which are given are the factored load. Okay, so we are not supposed to multiply by 1.5, so directly we have to given. Okay, so I'll draw the typical sketch of this. This is the column, where now B, this will be the smaller dimension, we have to assume as B. Okay, and this is D. So ultimately it equals to 400 mm, and this will be 600 mm. Okay, so in some of the books you will find, you may write it as a capital D, or you can write it as capital D, best way, no problem. Okay, so capital D we will consider, because D dash is also coming, so I'll explain one by one. So this is capital D, okay, and small b. Okay, so first of all, it is to be designed for single curvature. Okay, then now factored load is given, which is 2000. I am writing the given data. Then MUX2, what is that? In top, larger end moment at top 220 kilonewton meter, and MUX1 is 170 meters. So in Newton, 220 into 10 to the power 3 Newton meter, 170 into 10 to the power 3 Newton meter. Okay, further if you can go it into meter, then again 220 into 10 to the power 6 Newton mm. 170 into 10 to the power 3 Newton mm. Sorry, it should be 6. Okay, so just like that, MUY2 also you have MUY2, then it should be 120 kilonewton mm, and MUY1 also we have 70 kilonewton meter. So it is 120 kilonewton Newton, 120 into 10 to the power 6 directly Newton mm, and 70 into 10 to the power 6 Newton mm. So this is what we have. Okay, and then capital L is given, effective length is 8 meters, so we will write it mm. Okay, then effective length in x direction it is given. What is that? 7.5 meter, 7500 mm, and LEY, that is the 6 meter, means 6000 mm. Okay, and the grade of steel is Fe415. The grade of steel is Fe415. Okay, so for the single curvature, then this is the given data we have assumed. Okay, and one thing here, the M grade is not given. Okay, so we need to assume it. So we will assume M25. Okay, assumed. So we'll assume M25. So our FCK will be 25 Newton per mm square. Okay, now in this step there is a very important assumption. In this step, that is the assumption of D dash. Okay, though in the steps when we have seen, I have just kept here small d, but it's all about our nomenclature assumptions. So D dash we need to assume. While assuming D dash, you should assume in a such a way that the D dash by D, the ratio of D dash by D should be identical in table, should be identical. Okay, so here we have 600, so 0.1 we have a chart, so we'll assuming the D dash equals to 60 mm. Okay, so that D dash by D, 60 by 600 should be 0.1. So this value we will require, and this value will be useful for further calculation. Okay, so this is all about, and we need to be very meticulous and very serious regarding selection of this. Okay, so I assume this 60. You can assume 35, 45, 50, but try to understand the value. This value should be identical, 0.1, 0.15, 0.2, so that it is easy for the to pick the value from the graph which is available with the numerical. There is the interpolation chart, and this graph should be, there is an interaction chart, and this should be available with the numerical only. Okay, so this is all about the first step. So now our next step will be check for slenderness. So by this step we will decide whether the column is long or short. So it's a very important step. So number one, the LEX upon capital D. So LEX we have 7500. Now I'm using mm upon 600. So this ultimately coming to 12.5. So it is greater than 12. So hence the column is long in x direction. So hence additional moment should be calculated. Okay, now next step, again LEY upon small b. So 6000 upon 400, so it is coming 15, so it is also greater than 12, so we need to write it down again. Hence the column is long in y direction, so additional moment should be calculated. Okay, should be calculated. So the next step will be, after deciding this, next step calculation for final design moments. Okay, that is MUX and MUY. So here there is a part A. Part A will be to find initial design moments. So this is very important step after the check for slenderness. It is very important, and we need to very seriously check out these parameters. So for in the final design moments we have part A, and in part A first will be moments due to minimum eccentricity, moments due to, that is MUX minimum and MUY minimum. Okay, so we have again two conditions for that. Then E minimum X is equals to, either you should assume 20 L by 500 plus D by 30, which is coming to 8000. The length is given in mm upon 500 plus D we have 600 upon 30. Either this value, or you need to minimum 20 mm. Okay, so it is coming to 36 mm, and we need to pick the maximum value. So E minimum X E minimum X equals to 36 mm. So similarly we need to go for E minimum Y. So again E minimum Y equals to L by 500 plus now small b upon 30. So L is, we have 8000 plus 500 plus small b we have 400, then 30. So either this or this 20 mm minimum. So we need to pick maximum of 2. So it is coming out to be 29.33. So E minimum Y is 29.33 mm. 29.33 mm. Okay, so finally MUX minimum equals to PU into E minimum X direction, that equals to, we have 2000 into 10 to the power 3, I'm using in newtons, into this 36. So it is coming to, in the meantime you should do this value in your calculator. MUY minimum P into ultimate load into E minimum, that is Y. Now that equals to 2000 into 10 to the power 3, we are using in newtons, and this value is in the y direction, 29.33 now. So it is coming out to be 72 into 10 to the power 6 Newton mm, and this is coming out to be 58.7 into 10 to the power 6 Newton mm. So by this way we have got the value of mux minimum here and muy minimum here. Okay, so I hope you understood this step. So now our next step will be moments due to external end moments. Okay, so that means top end moment and bottom end moment. Top end moment and bottom end moment. I am writing this because these values are given in the numerical. Okay, and now column is bending in the single curvature as it is given in the numerical only, so we are supposed to use the plus signature. Okay, so mix is equals to 0.6 of mux2 plus 0.4 into mux1. So we have 0.6 mux2, we have 220 into 10 to the power 6 Newton mm plus 0.4 into 170 into 10 to the power 6 Newton mm. Okay, so it is coming out to be something 200 into 10 to the power 6 Newton mm. Okay, Newton mm. So there is a one check, this value should be greater than or equal to 0.4 times of mux2. Okay, so it is 0.4 times of mux2, so it is coming out to be something 88 something 10 to the 88 into the power 6 Newton mm. So from this first and this second we need to choose maximum one, so our mix will be 200 into 10 to the power 6 Newton mm. So we have made this value here. Similarly we have to go for miy. So miy equals to 0.6 into muy2 plus 0.4 into muy1. So 0.6 into what is value muy2, 120 into 10 to the power 6 plus 0.4 into value of 70 into 10 to the power 6. Okay, so it is coming out to be something 100, okay, into 10 to the power 6 Newton mm. This value is also greater than or equal to, should be 0.4 times of muy2. So it is coming out to be something 48 into 10 to the power 6. So from this first value and second value we will choose the maximum one. So miy equals to 100 into 10 to the power 6 Newton mm. In the previous lecture I have tell you the brief steps, so it is very easy to understand if you have gone through all the steps. Okay, and then after this, thus the initial design moments are okay, so mux will be the greater value of mux minimum and mix. So I think this value is greater. Okay, looking towards it, so it should be 200 into 10 to the power 6 Newton. And similarly muy equals to greater value of muy minimum and miy. So I think it is 100 is greater. We have both the calculation is in part A and part 1. Okay, so we have got the initial design moment. So initial design moments mux and muy, it is 200 into 10 to the power 6 Newton mm and 100 into 10 to the power 6 Newton mm. So these are the final calculations, and by this way we have got the initial design moments. I hope now you understand the step. So now next part B, to find the additional moments due to slenderness. Now this step is exclusively for long columns, that is MAX and MAY, additional moments we need to calculate. Okay, MAY. So here we have calculation. Now calculation for reduction factor, that is K. We need to calculate. We have two parameters, Kx and Ky. Okay, now the very important step is there, and that step is, now we have to assume the percentage of the steel for which the entire calculation is going. So now we have seen in the previous steps how to know what is the range, assuming the percentage of reinforcement, as a steel, you can say. So now we'll assume, let us say for 2.5%. generally it can assume from 1 to 4%, maybe 2.5u, 3.5u or 3%, you can assume, no problem, depend upon trial. So we have assumed that it is 2.5% with equal reinforcement, okay, along periphery. Periphery means that is reinforcement is distributed equally on four sides. Equal distribution has to be there. So now we'll have steps. Asc equals to percentage of Ag. So what is the percentage? I must write like this, percentage of reinforcement of Ag, like this. So we have some 2.5% of gross area, that is, so 2.5 divide by, as it is in percentage, so 400 into 600. So Asc is coming out to be 6,000 mm square. So it is, we have Asc equals to percentage of steel of gross area, so it is 2.5% into B into D. So AC next step will be Ag minus Asc. Okay, so what is the value of Ag? Ag is B into D. Okay, minus 600. So what is, Ag is what is Ag? B into D minus Asc we have, that is 6,000. No need to write unit now. Okay, so it is 400 into 600 minus 6,000. So it is coming to be 234 into 10 to the power 3 mm square. Okay, so, and you know that plus Asc, from this formula we can derive this. Okay, no problem. Now we require three parameters, such as number 1 will be Pu, which is 2000 into 10 to the power 3 Newton. Then Puz equal to 0.45 FCK into AC plus 0.75 Fy into Asc. So this formula you will get in page number 71 of IS 456. Now put the value here, 0.45 into 25 into 234 into 10 to the power 3 plus 0.7 into 415 into F. See, we have calculated 6,000. Now what is the value coming to be? 4.5 into 10 to the power 6 Newton. So now we need to calculate the value of PBX. So both the cases we'll try. Now 3 PBX. So for that we require 4 value, 1, 2, 3 and 4. So what is D dash by capital D? Whatever D dash, 660 by 600, it is coming to 0.1. Then from table we'll pick the value of K1x and K2x from table 0.3. Sometimes this table is provided with the numerical 0.30328. These values I am from table. Okay, from table. And now PBX equals to K1x plus K2x into percentage of steel divided by FCK into FCK into B into D. Now you must put the value 0.207 plus, what is the value of K2? 0.328 from table into 2.5 divided by 25 into 25 into 400 into 600. So it is coming to be 1.4388 10 to the power 6 Newton. So we have got PBX. Similarly, we need to go for PBY. For this also we required 4 parameter A, B, C and D. So now D dash by B. What is the value of D dash? It is 60 by 400. It is coming to be 0.15. Now K2Y and K1Y and K2Y, these values are 0.196 and 0.203. that is from table. Okay, from table. And now finally PBY equals to 0.196 plus, directly I am putting the value K1Y, or I write it the formula K1Y plus K1Y plus K2Y upon percentage plus FCK into FCK B into D. So directly put the value here, 0.196 plus 0. It should not be plus here. Okay, it is plus there. You need to be very careful regarding this overwriting and this all I am about to. Okay, 0.196 plus 203 into 2.5, that is we have assumed, and 25 FCK bracket close into 25 into 400 into 600. So it is coming to be 1.2978 10 to the power 6 Newton. So here we have got this and here we have got this. So I hope you have understood the steps. Okay, so the reduction factor Kx equals to PUZ minus PU upon PUZ minus PBX, and similarly Ky is equals to reduction factor Y, PUZ minus PU upon PUZ minus PBY. So just put the value here. What is the value of PUX? 4.5 into 10 to the power 6 minus 2000 into 10 to the power 3 divided by 4.5 into 10 to the power 6 minus 1.4388 10 to the power 6. So it is coming to be 0.18817. So it is also less than equals to 1, so it is okay, safe. Now hence here again same, put the value. What is the value of that? 4.5 into 10 to the power 6 minus 2000 into 10 to the power 3. These values are given, pu. Then again 4.5 into 10 to the power 6 minus 1.2978 into 10 to the power 6. So this value is also coming 0.78, which is less than 1. So it is okay, safe. Okay, so now calculation for additional moments. Calculation for additional moments, that is additional moments mx, moment additional x. So that is pu into d by 2000, formula is 2000 into lex by capital D into kx. So now put the value 2000 into 10 to the power 3, the D is 600 upon 2000 into 7500 mm in mm. Okay, it has to be square, and the value of reduction factor is 0.817. So it is coming to be 76.59 into 10 to the power 6 Newton mm. Okay, additional moment. So this is the additional moment. Now for y, in y direction, y, so pu into b, so you will get d in place of x and b in place of y. So wherever there is a y term, you will get small b, there is x term, you will get capital D. So it is easy to recall, LEY, effective length in y direction, upon small b whole square into ky. So 2000 to 10 to the power 3 into, it is 400. It is 400 divided by 2000 into 6000 divided by 400. I'm taking values in mm, square into 0. This value we have calculated 78. Now it is coming to be 70.2 10 to the power 6, okay, Newton mm. So value of additional moment y, it is coming to be 70.2. Okay, so this is all about this calculation of additional moments. So I hope you understood this step. So now thus our final design moments are mux is equals to mux, whatever we have calculated in part A, plus additional moments of B. So it comes to 200 in part A, we have calculated to power 6, plus just now we have calculated it 59 and to the power 6. So it is coming to be 276.59 into 10 to the power 6 Newton meter. Now this value is greater than our mux2, which is 220, okay, Newton mm 10 to the power 6. So it is okay. If the value is coming less than it, so then we need to redesign the numerical by taking the other assumptions. So mux equals to 276.59 10 to the power 6 Newton mm. Similarly for MUY of A plus additional moment at Y of B. Okay, so it is 100 10 to the power 6 Newton, not here, we are just putting the values, and just now we have calculated 70.2 into 10 to the power 6, so it is coming to 170.2 into 10 to the power 6, which is also greater than MUY2, which is 120 into 10 to the power 6. So it is greater, so it is okay. So your MUY equals to 170.2 into 10 to the power 6 Newton mm. Okay, so this we have calculated. So now finally we have done with moments, which is we have ultimate load of this Newton 10 to the power 3 Newton. Then MUX, this should be X, MUX should be 276.59 into 10 to the power 6 Newton mm, and MUY is 170.2 into 10 to the power 6 Newton mm. Now we need to use further, so this we are using for further calculations. Okay, so these are the very important part. Hereafter there is a interaction chart. We will see interaction. So for that our next step will be calculation for MUX1 and MUY1, okay, with the help of interaction chart. So this chart will be available with you in the examination. I'll show you how to choose the values and how to pick the values. So the major assumption is, assume the percentage of reinforcement, as we assume 2.5% with equal reinforcement, okay, along periphery. So now first part we'll see, and so for this we require the 4 parameter to find MUX1, and here we will see to find MUY1. So we required 4 values, let us say B, C and D. So first one, D dash by D, what is 60 upon 600, it is 0.1. Then PU upon FCK BD. Okay, so this is 2000 we have upon FCK 25 into 400 into, so it is coming to 0.33. Okay, now again load upon the FCK percentage, sorry, not load, percentage. So 2.5 by 25, it is coming to 0.1. And finally we require this value MUX1 by FCK BD square. This value we need from the chart. So we'll see the exact value how to pick from chart. Okay, so I'll explain one example how to pick from the chart. So I'm searching it, interaction curve. Okay, so this is the interaction curve. You can see this is the interaction curve. You can see here where this y-axis is known for PU upon FCK BD, where this value we have PU upon FCK 0.33. This is the scale. Then we have the value which is, we know we need to calculate it, MU upon FCK BD square. So we don't know where this curve lines is of the D dash by D. Okay, so we need to pick up this, we need to choose this table from this D dash by D. Okay, it is 0.1. So we have 0.1. So our table is correct. You can see table is correct. Then PU upon FCK. So this is X. So this is upon X axis. Sorry, this is Y axis. In Y axis we have PU upon FCK BD. We have 0.33. And then our line is of 0.1. These curved lines stand for P upon FCK. Okay, percentage of the reinforcement upon FCK. So we have 0.33. So our 0.33 is lies something here. I will mark here 0.33, and our now we'll go in this direction. Okay, 0. And now our line, our curved line is 0.1. So we'll have 0.1 here. This is the curve of 0.1. So this is the curve of 0.1. You can see I am overwriting it. This is the curve. So I'll draw line. So here it will intersect. So I'll take one perpendicular line here. So it is something around 0.123. Okay, 0.135 something. Okay, here it is between 0 to 112. So 0.1, 0.11, 0.12, 0.13, and here in between, so it should be 0.135. Okay, so this your chart we have taken 0.135. so by this way, same procedure we have to follow for the y also. Okay, so same thing we have to repeat again in case of y. So again, so I hope you understood the concept how we have chosen the value. Okay, now so mux1 is equals to 0.135 into cross multiplication fck bd square. So 0.135 into 25 into 400 into 600 square. So it is coming to 486 point, okay, dot 00 into 10 to the power 6 Newton mm. Okay, Newton mm. All right. So similarly, now again for y1 a, then b, then c, and then d. So d dash by b. Now what is the value of d dash? D dash 60 by 400. So it is the value coming to 0.115. So now that chart is not useful for us because that is for 0.1. So you need to choose another chart. Chart will be provided to you in the examination. Then pu upon fckbd, it is 2000 upon, same value is there, 10 to the power 3 upon 25 into 400 into 600. So it is coming to 0.3, the same as just now. Then percentage of reinforcement upon fck, so it is coming to, it is also 0.1. now muy1 upon fck b square d. Now this value we will pick from the chart with the same procedure whatever I have explained you just now. So it comes to 0.121. Okay, so muy1 equals to 0.121 into fck b square d. So 0.121 into 25 into 400 square into 600. So it is coming out to be 290.4 into 10 to the power 6 Newton mm. So I hope you understood this step. Okay, so by this way we have got the value. Okay, now our next step with this will be calculation for alpha n. Okay, now so this also you will get by in page number 71, if page 71 of IS 456. Okay, so for this we require again 4 parameters. Okay, that is, the first one will be ultimate load, then second will be the PUZ, then third will be PU upon PUZ, the ratio of PU upon PUZ, and finally the value of alpha n. Okay, so we have ultimate load 2000 into 10 to the power 3 Newton. PUZ we have 4.5 into 10 to the power 6 Newton, and the ratio is coming to 2000 into 10 to the power 3 divided by 4.5 into 10 to the power 6. So it is coming out to be 0.44. Okay, so what is the value of alpha n? So sometimes interpolation we need to see, and I can tell you if the ratio of pu upon puz is lies between 0.2 to 0.8, then we have to go for interpolation. For example, the value of pu, the ratio of pu upon puz is less than or equal to 0.2, then we need to pick the value is equals to 1. And if the ratio of pu upon puz is less than or equal to 0.8, then we need to take the value of alpha n equal to 2. But now it is coming between 0.2 and 0.8, so we need to go for the interpolation. Okay, so we'll do with the interpolation. It is coming out to be 0.44. So 0.2, 0.44 and 0.8. That is x1, that is x, and that is x2. So for 0.2 we have 1, for 0.8 we have 2, and for y we need to calculate. So by doing the interpolation, y equals to y1 plus y2 minus y1 upon x2 minus x1 into x minus x1. So y1 equals to 1 plus 2 minus 1 upon 0.8 minus 0.2 into 0.44 minus 0.2. So the value of y is coming to be 1.4. So alpha n equals to 1.4. I hope you understood the step now. Now then, very important, then check for safety of the bilective. Then check for safety of biaxial bending. Check for safety of biaxial bending for our assumed percentage, that is 2.5. Okay, so this will be mux upon mux1 in bracket whole square alpha n to the power alpha n plus muy upon muy1 to the power alpha n. Now this value should be less than or equals to 1. So now we'll see and we'll check it out. 276.59 into 10 to the power 6 divided by 486.0, exact we have got the value 0, 486. So I'll write this 486.10 to 1.4 plus 170.290.4 into 10 to the power 6, that is 1.4. Now it is coming to be, put the values, 0.927. so it is less than 1. So hence it is safe for 2.5 percentage of steel. It is okay. I hope you understand. It is very crucial check and we have passed it. Okay, now our next step will be of design of longitudinal reinforcement, that is AS. Okay, so now we know AS equals to the percentage of steel into AG, gross area. So 2.5% into the cross section, that is 400 into 600. We know AG equals to B into D. So 2.5 by 100, as it is in percentage, 400 into 600. This step we have also done previously. It is coming to be 6000 mm square. So assuming the number of bars, then assuming the, let us say 12 number of bars. So let us calculate the area, then n into the pi square by 4, so we have 12. Okay, and then we know this 600, so we need to calculate the diameter. So the phi is coming to be 25.33. so let us round it up or assume 26 mm. So phi equals to 26 mm. So we can write it as, thus provide 12 bars of 26 mm phi. Okay, so basically bars provided in the longitudinal reinforcement should be greater than the 12. Okay, and then next we have design of transverse reinforcement. So I write here, after I write here, design of transverse reinforcement. Okay, that is link or lateral ties. Then I'll shift here the space I have made work. So part A, your diameter of the link. Diameter of link. Though I am telling you all these possibilities steps, but you follow only one in the exam, it's okay. So part 1, your diameter of link, I'll write a short dia of link equals to 1/4 by 5. So 1/4 into 26, so it is coming to be 6.5 mm or 6 mm or 6 mm. So we need to pick the maximum value, so we'll pick this. So okay, so dia of link will be 6.5. so practically 6.5 not possible to critical, so we'll round it up to say 8 mm. Okay, so diameter of link equals to 8 mm. 8 mm. Okay, now the part B I'll write here. Okay, part B I'll write here, and then part B. So pitch of link, pitch of link. So we have 3 formulas for that. We have 3 formulae. Either pitch of link, pitch, I write first pitch of link, pitch of link, and pitch of link. So we have 3 conditions. We need to pick the minimum one. Okay, remember, first one will be the least dimension, that is B. We have 400. Then second will be 16 times 5. We have 16 into 26 into 16. So we have and or minimum should be 300 mm. So either it should be minimum 300 or minimum dimension, or it is coming to be 416 mm. So minimum will choose this value. Okay, so pitch of link equals to minimum of 3, that is 300 mm center to center. Okay, so we have to write it down. Thus provide pitch of link, that is equals to 300 mm center to center. Okay, now finally the very important and very crucial for valuation examination point of view, to get full out of full marks, the details of reinforcement. Details of reinforcement. So it's not as complicated as water tank, it is very simple. So just draw a proper rectangle. Okay, I hope you are using scale. Draw the proper rectangle. Okay, then this will be the smaller dimension, this will be the greater dimension. So we have, this is 600 mm, this is, we have 400 mm, and now inside that we are supposed to provide the reinforcement. So we have provided okay, 1 2, I'm drawing this, it is spacing should be proper, 3 4. Okay, this way. Then again there is 2. Okay, so we have provided the 12 bars, 1 2 3 4 5 6 7 8 9 10 11 12. So here we have provided the 12 bars. Okay, so just we need to draw this like this. Yes, again and this. Okay, so now these are our bars, so that is 12 number of bars, 12 bars of 26 mm diameter, that is the longitudinal reinforcement. Okay, and these are the 8 mm lateral ties we have provided, 8 mm phi at 300 mm center to center. That is the lateral ties. Okay, so we have this drawn first, this. Okay, then you must use proper scale and proper dimensions. Just I have parallelly drawn this while explaining, so it is not as good as it should be, but you should explain and ensure that proper scale pencil and proper dimensions. So these are the 1 2 3 4 5 6 7 8 9 10 11 12 number of bars at 26 mm diameter. Then lateral ties we have provided. Okay, lateral ties at 8 mm. So this is all about the reinforcement details, and I hope this is the concluding step, and I hope you understand the design of a long column subjected to biaxial movements. Okay, thank you very much.